Imagine standing at the edge of something so vast, so violently powerful, that the very concept of safety dissolves into irrelevance. Not a battlefield, not a storm, not a volcano on the verge of eruption. Something far more ancient, far more indifferent, and far more lethal than anything humanity has ever constructed or survived. Imagine a place where the air itself, if there were air, would cook you from the inside out in seconds. Where the energy raining down on you carries so much force that it doesn't just burn flesh or blind eyes. It tears through the very structure of your DNA. It snaps the ladder of life itself, rung by rung, until there is nothing left that resembles a living thing. These places exist. They are not fiction. They are not the invention of science fiction writers or the exaggeration of doomsday prophets. They are real, documented, studied by some of the most brilliant minds humanity has ever produced, and they are scattered throughout the universe with a breathtaking, terrifying abundance. We are talking about the lethal radiation zones of the universe. And before this story ends, you will never look at the night sky the same way again. Here is something that most people never stop to consider. When you step outside on a clear night and tilt your head back and allow your eyes to adjust to the darkness, you are looking at a graveyard of violence. Every single point of light you see, every star, every faint smear of a distant galaxy, is a furnace of nuclear energy, a machine of annihilation operating on a scale that makes our most powerful nuclear weapons look like birthday candles. The universe does not care about life. The universe does not nurture or protect or preserve. It simply exists, and in its existence, it produces energies and forces so extreme that entire solar systems can be rendered uninhabitable in an instant. Radiation is not just a side effect of these processes. In many cases, it is the primary product. It is the currency of the cosmos. And we, small and fragile and made almost entirely of water and carbon, are walking into a conversation that has been happening for 13.8 billion years without us. So let us begin at the beginning. Not the beginning of radiation as a human concept, not Marie Curie's laboratory or the Manhattan Project or Chernobyl's reactor number 4, but the actual beginning. The cosmic beginning. Because to understand the lethal radiation zones of the universe, you need to understand that radiation itself is not an aberration. It is not something that went wrong. It is woven into the very fabric of creation. When the universe was born, and that word born is almost insultingly gentle for what actually happened, it was not a quiet event. The Big Bang was not an explosion in the conventional sense because there was no space for it to explode into. It was instead the sudden and simultaneous appearance of all space, all time, all matter, and all energy in a single, incomprehensible instant. And in that first fraction of a second, the universe was nothing but pure, unimaginable radiation. The temperature was so extreme, we are talking about numbers so large they become almost meaningless, that matter itself could not exist. Protons and neutrons could not form. Atoms were impossible. There was only energy, only photons, only a blazing, roaring sea of electromagnetic radiation in its most ferocious state. This is the universe's original condition. This is what it looked like before anything else existed. A zone of pure, lethal radiation so intense that no physical structure of any kind could survive within it. As the universe expanded and cooled over hundreds of thousands of years, matter began to condense out of that primordial radiation. Hydrogen atoms formed, then helium. Then, over billions of years, gravity pulled these gases together into the first stars, and those stars lit up the universe again. Not with the same primordial radiation, but with nuclear fire. And it is here, in the hearts of stars, that our story truly begins. Because a star is, at its core, a radiation factory. Every second, the sun at the center of our solar system converts about 600 million tons of hydrogen into helium through nuclear fusion. And in doing so, it releases energy, photons of light and radiation, in staggering quantities. The sun radiates about 3.8 times 10 to the power of 26 watts of energy. That number is so large it is functionally incomprehensible. If you tried to power the entire United States electricity grid with that energy, you would have more power than you could use if everyone on Earth were trying to drain it simultaneously for the next billion years without making a dent. Before we go further, ask yourself this. If the sun, our friendly neighborhood star, the thing that grows our food and warms our oceans and makes life on this planet possible, if that star is essentially a nuclear radiation machine of incomprehensible power, what then exists in the universe that makes the sun look tame? What places exist out there, in the deep dark between the galaxies, that make our star seem like a candle in a hurricane? The answer to that question is the heart of this documentary. And I promise you, by the time we are finished, you will have a fundamentally different understanding of what the universe actually is. Let us start close to home. Let us start with the sun itself, because the sun, for all its life-giving warmth, has a side to it that most people never fully appreciate. The surface of the sun, the photosphere, burns at about 5,500 degrees Celsius. That is already beyond anything we can easily conceptualize. But the corona, the sun's outer atmosphere, somehow reaches temperatures of over 1 million degrees Celsius, a phenomenon that baffled physicists for decades and still does not have a fully satisfying explanation. From this roiling, superheated environment, the sun constantly streams particles outward in what we call the solar wind, a continuous flow of protons, electrons, and alpha particles traveling at speeds of up to 800 kilometers per second. This solar wind carries radiation in multiple forms, including X-rays and ultraviolet radiation, and it fills the entire solar system with a bubble of charged particles called the heliosphere. If you were standing on the surface of Mars without any protection, the radiation levels would be approximately 17 times higher than on Earth's surface, primarily because Mars has lost most of its magnetic field and its atmosphere is too thin to provide meaningful protection. NASA scientists studying data from the Curiosity rover found that an astronaut on the Martian surface would be exposed to about 0.7 millisieverts of radiation per day. A number that sounds small until you realize that is roughly equivalent to getting a full-body CT scan every 5 to 6 days. Over a 2.5-year Mars mission, that exposure adds up to about 1 sievert of radiation, the dose at which your lifetime cancer risk begins to increase significantly, and the dose at which some regulatory bodies classify exposure as dangerous. And Mars, remember, is still within the protective bubble of our own star's magnetic influence. Now step outside the heliosphere. Step into interstellar space, the cold, dark space between solar systems, and the radiation environment changes dramatically. You encounter galactic cosmic rays, high-energy particles, mostly protons and atomic nuclei, that travel through the galaxy at velocities approaching the speed of light. These particles have been accelerated to extraordinary energies by supernova explosions, and they stream through the galaxy in all directions, carrying energies millions of times greater than anything our most powerful particle accelerators can produce. Inside the heliosphere, the solar wind provides some shielding against galactic cosmic rays. Outside it, you are fully exposed to them. And galactic cosmic rays are particularly insidious because they are not just radiation in the conventional sense. They are particles with so much momentum that they pass through ordinary matter as if it barely exists, shattering atomic nuclei along the way and producing cascades of secondary radiation. A thick enough layer of water or lead can slow them down, but stopping them entirely requires enormous quantities of shielding material. Far more than any spacecraft we have ever built can practically carry. But cosmic rays from within our galaxy, as dangerous as they are, represent only a fraction of the radiation story. Because there are objects in the universe that produce radiation on scales that redefine the word extreme. And we need to talk about them in detail, because each one is its own unique variety of lethal magnificence. Let us talk about pulsars. A pulsar is what remains when a massive star, one with a mass between about 8 and 20 times the mass of our Sun, exhausts its nuclear fuel and collapses under its own gravity in a catastrophic supernova explosion. The outer layers of the star are blasted outward with unimaginable violence, and the core collapses inward, crushing a mass greater than our Sun into a sphere roughly 20 kilometers across. To put that in perspective, the Sun is about 1.4 million kilometers in diameter. A neutron star, the object left behind, is about 20 kilometers in diameter. That is the difference between a football stadium and a single coin. All the matter that was once the core of a star larger than our Sun is now compressed into something roughly the size of a city. The density of a neutron star defies easy comprehension. A single teaspoon of neutron star material would weigh about 10 million tons. The gravity on the surface of a neutron star is about 200 billion times stronger than Earth's gravity. If you tried to stand on the surface of a neutron star, and the word stand is being used very loosely here, given that you would have been compressed into a layer thinner than an atom long before reaching the surface, the gravitational force would be so extreme that it would play a measurable role in warping the space around the star, as Einstein's general relativity predicts. Now here is where it gets extraordinary. When the core of a massive star collapses into a neutron star, the collapse is so rapid and so violent that it dramatically amplifies the star's magnetic field. The original star's magnetic field, already powerful, is compressed along with everything else, and the result is a neutron star with a magnetic field billions of times stronger than anything we can produce in a laboratory, and trillions of times stronger than Earth's magnetic field. And because this collapsed core is rotating, conserving the angular momentum of the original star the way a spinning figure skater speeds up when pulling her arms in, it can spin incredibly fast. Some neutron stars rotate hundreds of times per second. The fastest known pulsar, PSR J1748-2446 AD, discovered in 2004, spins at 716 rotations per second. That is faster than a kitchen blender. This combination, extreme density, extreme magnetic field, extreme rotation speed, creates something remarkable and terrifying. The magnetic field of a pulsar is not aligned with its rotation axis. Much like Earth's magnetic poles are not perfectly aligned with Earth's geographic poles. As the pulsar rotates, its magnetic poles sweep around, and the radiation they produce, intense beams of X-rays and radio waves emitted from the magnetic poles, sweeps through space like cosmic lighthouses. Every time that beam passes across our line of sight, we detect a pulse. Hence the name, pulsar. But here is what you need to sit with for a moment. Those beams of radiation are not gentle at close range. And what counts as close range here is relative. The radiation from a pulsar would be instantly lethal to any life form we know of. The X-ray luminosity of some pulsars equals or exceeds the total electromagnetic radiation output of our entire Sun, compressed into a narrow beam, sweeping through space at the speed of light. If a pulsar's beam were aimed directly at Earth from within a few light years, the consequences would be catastrophic. The radiation would strip away the ozone layer in a geological instant, exposing the surface to ultraviolet radiation levels that would sterilize it. Some researchers have speculated that such an event in Earth's past might have contributed to mass extinction events, though this remains a hypothesis rather than established fact. The closest known pulsar to Earth is PSR J0108-1431, located about 420 light-years away. At that distance, and given the random orientation of its beams, we are not in any immediate danger. But the fact that such objects exist, rotating, radiating, sweeping the galaxy with lethal beams, is itself a startling thing to contemplate on a quiet evening. Now let us take this further. Because neutron stars, as extraordinary as they are, can be pushed to even more extreme states. Some neutron stars, produced in particular types of supernova events, end up with magnetic fields so powerful that they dwarf even ordinary pulsars. These objects are called magnetars, and they represent one of the most extreme forms of matter and energy in the known universe. A magnetar's magnetic field can reach 10 to the power of 11 Tesla, 10 billion times stronger than the strongest magnetic fields we can produce in laboratories on Earth. To put that in context, a magnetic field of about 45 Tesla is enough to levelize the atoms in a human body due to the quantum mechanical properties of electron orbitals. A magnetar's field is more than 2 billion times stronger than that. On December 27, 2004, astronomers detected what is now considered one of the most powerful cosmic events ever recorded from outside our solar system. A magnetar called SGR 1806-20, located about 50,000 light-years away on the other side of our galaxy, experienced what is known as a giant flare, a catastrophic rearrangement of its magnetic field structure that released, in a single tenth of a second, more energy than our Sun produces in 300,000 years. Let me repeat that, because it deserves to be stated clearly. In 1/10 of a second, a single magnetar released more energy than our Sun produces in 300,000 years. The resulting burst of gamma radiation, the most energetic form of electromagnetic radiation, was so intense that it briefly saturated the instruments of multiple satellites designed specifically to detect such events, even from 50,000 light-years away. It measurably ionized the upper atmosphere of Earth. It created detectable effects on our planet from half the diameter of the Milky Way away. Pause here and think about that. If that magnetar had been located 1 light-year from Earth instead of 50,000, the gamma-ray burst it produced would have delivered a dose of radiation to Earth's surface sufficient to cause a mass extinction event. If it had been located within 10 light-years, the Earth's atmosphere would likely have been stripped away entirely, and the surface would have been sterilized within minutes. One of the most violent events in recorded cosmic history happened 50,000 light-years away, and it still affected our planet. That is not a frightening hypothetical. That is a documented historical event that occurred within living memory. But we have not yet reached the top of the hierarchy of cosmic radiation sources. Not even close. Because there is a class of events so powerful that astronomers, when they first detected them, genuinely believed they might be signals from an alien civilization. Simply because nothing in their knowledge of astrophysics could account for something that bright, that energetic, that overwhelming. These events are called gamma-ray bursts, and they are, by the broadest consensus of the astrophysical community, the most powerful explosions in the universe since the Big Bang itself. Gamma-ray bursts were first discovered by accident. During the Cold War, the United States deployed a series of military satellites called VOID satellites, designed to monitor for nuclear weapons tests by the Soviet Union. The VOID satellites were equipped with sensors capable of detecting gamma radiation, the kind produced by nuclear explosions. In 1967, these satellites detected a burst of gamma radiation unlike anything their designers had anticipated. It did not match the signature of a nuclear test. It came from space. Over the following years, more bursts were detected, always from seemingly random directions in the sky, always enormously energetic, and always brief, lasting anywhere from milliseconds to a few minutes. This bizarre mystery consumed the astrophysics community for decades. Scientists argued about their nature, their distances, their mechanisms. Were they within our galaxy or far outside it? Were they truly as energetic as they seemed? The mystery began to unravel in the 1990s when the Compton Gamma Ray Observatory, launched in 1991, detected thousands of gamma-ray bursts and confirmed that they were distributed isotropically, equally in all directions, across the sky, strongly suggesting they were extragalactic, coming from far outside the Milky Way. The final confirmation came in 1997 when astronomers were able to identify afterglows, fading optical and X-ray emission following the gamma-ray burst, and measure the redshifts of their host galaxies. The distances were staggering. These events were occurring billions of light-years away, which meant that if they could be detected across billions of light-years with instruments in Earth orbit, the actual energy output of these events must be incomprehensibly large. And indeed it is. A typical gamma-ray burst releases in a matter of seconds the equivalent energy of our Sun over its entire 10 billion-year lifetime. The most energetic gamma-ray bursts release energy equivalent to thousands of suns burning for their entire lifetimes, all compressed into a beam of gamma radiation that lasts for perhaps a minute. Some gamma-ray bursts are so luminous that, if they occurred within our galaxy and were aimed in our direction, they would be visible in daylight with the naked eye, even from thousands of light-years away, for a few seconds, before the gamma radiation arrived and killed everything on the sunlit side of the Earth. There are two main types of gamma-ray bursts, and they arise from different physical mechanisms. Short gamma-ray bursts, which last less than 2 seconds, are now understood to result from the merger of two neutron stars, or a neutron star merging with a black hole. These collisions happen when two massive stars in a binary system both go supernova, leaving behind two neutron stars that spiral together over millions of years, radiating energy as gravitational waves, until they finally collide in a cataclysm of relativistic jets and gamma radiation. The collision also produces enormous quantities of heavy elements, gold, platinum, uranium, through a process called the R process, or rapid neutron capture. Every piece of gold jewelry you have ever seen or worn was forged in the death collision of two neutron stars billions of years before our solar system was born. That is not a metaphor. That is the literal truth. Long gamma-ray bursts, lasting more than 2 seconds and sometimes several minutes, arise from a different mechanism. The death of an extremely massive star, one perhaps 100 times the mass of our Sun, in a hypernova. A supernova so powerful it makes a normal supernova look modest. When the core of such a star collapses directly into a black hole, the infalling material forms an accretion disk, and the magnetic fields in rotation create focused jets of plasma and radiation that punch through the collapsing star and extend into space as beams of gamma radiation. These jets travel at more than 99.9% of the speed of light, and the gamma radiation they carry is so energetic that individual photons carry billions of times more energy than the photons of visible light. In 2022, astronomers detected a gamma-ray burst that shattered all previous records. Designated GRB 221009A, it was immediately nicknamed BOID, the brightest of all time. This burst, which occurred in a galaxy about 2 billion light-years away, was so extraordinarily bright that it saturated virtually every gamma-ray detector currently in orbit. Scientists are still analyzing the data, and what they are finding is remarkable. GRB 221009A appears to have been roughly 100 times more energetic than the previous most extreme gamma-ray bursts ever observed. Its afterglow was detectable for an unprecedented length of time, and it produced photons of such extreme energy, reaching into the tera-electron-volt range, that their very existence poses questions about our understanding of fundamental physics. Some models of quantum gravity predict that very high-energy photons should travel slightly slower than lower-energy photons, and the detection of GRB 221009A allowed researchers to place the tightest ever constraints on this prediction, with profound implications for our understanding of space-time itself. Now here's a question worth asking yourself as you sit with this information. If the universe is producing these events constantly, and it is, astronomers estimate that at least one gamma-ray burst occurs somewhere in the observable universe every day, then what are the odds that a gamma-ray burst has, at some point in Earth's history, pointed its beam at our planet? And what would that have meant? This is not a purely hypothetical question. Several researchers have seriously proposed that a gamma-ray burst may have triggered one of Earth's mass extinction events. The leading candidate is the Ordovician extinction, which occurred approximately 445 million years ago and wiped out roughly 85% of marine species. The pattern of that extinction, which showed disproportionate loss of species in shallow, sunlit waters and near the poles, matches what would be predicted if Earth's ozone layer had been temporarily destroyed by an intense burst of ultraviolet radiation, allowing lethal UV to reach the surface. Astrophysicists Brian Thomas and Adrian Malott, among others, have published peer-reviewed research arguing that a gamma-ray burst originating from within our own galaxy, aimed at Earth, could produce exactly this effect. The burst would not need to be close. Even an event several thousand light-years away could, if beamed at Earth, deliver sufficient gamma radiation to destroy a significant fraction of the ozone layer. The ozone destruction would not be permanent. The layer would recover over a few years, but the window of elevated ultraviolet exposure could be sufficient to cause widespread ecological collapse, particularly for organisms that depend on phytoplankton in shallow ocean waters. This hypothesis remains contested. Not everyone in the paleontological and astrophysical communities accepts it, and direct evidence is difficult to produce, given that gamma-ray bursts leave no geological trace that we currently know how to identify. But the physics is sound, and the pattern of the extinction is consistent with what the model predicts. It is one of those scientific hypotheses that keeps coming back, because it keeps fitting the evidence in ways that are difficult to dismiss. But gamma-ray bursts and magnetars are not the only sources of extreme radiation in the universe. We have not yet talked about the regions around black holes, which produce some of the most sustained and intense radiation environments in the cosmos. And to understand those, we first need to understand something counterintuitive about black holes. They are not dark. Not always. In fact, active black holes that are currently consuming material, can be the most luminous objects in the universe. A black hole itself, by definition, emits no radiation. The event horizon is the boundary beyond which not even light can escape. But the material falling into a black hole does not simply fall in quietly. As matter, gas, dust, stars, spirals in toward a black hole under its gravitational influence, it forms a structure called an accretion disk, a swirling, flattened disk of material that orbits the black hole at incredibly high velocities. Friction and magnetic interactions within this disk heat the material to extraordinary temperatures, in some cases tens of millions of degrees, causing it to radiate intensely across the electromagnetic spectrum, from radio waves all the way to X-rays and gamma rays. The inner regions of an accretion disk around a supermassive black hole can be among the hottest and most radiation-intense environments in the observable universe. Moreover, in many active black holes, the magnetic field structure of the accretion disk, combined with the extreme rotation of the black hole itself, if it is a spinning black hole, described by the Kerr solution of general relativity, can generate focused jets of plasma and radiation that extend for thousands or even millions of light years from the poles of the black hole. These jets are called relativistic jets because the plasma within them travels at a significant fraction of the speed of light. The radiation produced by these jets, through a process called synchrotron radiation, where electrons spiral along magnetic field lines and emit photons, can include X-rays and gamma rays of extraordinary intensity. When one of these jets happens to point almost directly at Earth, we see the result as an object called a blazar. Blazars are the most luminous persistent sources of radiation in the universe. They can outshine their entire host galaxies, containing hundreds of billions of stars, by factors of thousands. Some blazars are so luminous that their radiation, traveling billions of light years to reach us, is still bright enough to be detected by telescopes as the dominant signal from that direction of the sky. If you were located anywhere within the jet of a blazar, and by anywhere I mean anywhere within a region that could be light years across, the radiation levels would be so extreme that no shielding material we can conceive of would protect you. The photon flux alone would destroy any chemical structure, any molecular arrangement, any organized information. There would be nothing left that could even register what was happening. The nearest known blazar to Earth is Markarian 421, located approximately 434 million light-years away. It is, even at that enormous distance, one of the brightest sources in the X-ray and gamma-ray sky, and it is one of the most studied blazars because it is close enough, in cosmic terms, to observe in detail. In 1996, Markarian 421 experienced a massive flare that briefly made it one of the brightest sources in the gamma-ray sky, and the flare raised serious scientific excitement. Not because it posed any threat to Earth at that distance, but because the speed of the variation in its brightness placed constraints on the size of the emitting region, revealing that the extreme radiation was being produced in a region not much larger than our solar system, despite the fact that the total luminosity exceeded that of 100 billion suns. Now let us shift our gaze. We have been looking, largely, at point sources, individual stars, individual black holes. But radiation does not only come from discrete objects. It also fills space in ways that are diffuse, pervasive, and inescapable. The universe is bathed in what cosmologists call the cosmic microwave background radiation, the afterglow of the Big Bang itself. This radiation, now cooled to about 2.7 Kelvin, just barely above absolute zero, and stretched to microwave wavelengths, fills every cubic centimeter of the universe uniformly. It is the most ancient light that exists, having been released when the universe was about 380,000 years old, and it carries information about the very early cosmos that no other observation can match. In terms of radiation hazard, the CMB is harmless at its current temperature, but it was not always harmless. In the early universe, when the CMB photons were far more energetic and the universe was far denser, They constituted an environment of lethal radiation in every direction. There was nowhere to hide. There was nowhere that was not inside the radiation zone. And here's something remarkable about the CMB that most people do not know. It creates an effective limit on how far ultra-high-energy cosmic rays can travel through the universe. This limit is called the Greason-Zatsepin-Kuzmin limit, or the GZK limit, named after the three physicists who independently predicted it in 1966. When a cosmic ray proton, remember, a particle traveling at nearly the speed of light, encounters a CMB photon, the interaction can produce new particles, specifically pions, in a process that drains energy from the cosmic ray. This means that protons above a certain energy threshold, about 5 × 10 to the power of 19 electron volts, cannot travel more than about 160 million light-years before losing most of their energy to CMB interactions. This implies that the highest energy cosmic rays we detect at Earth must have originated relatively close to us in cosmic terms, within about 160 million light-years, and that sources of extreme cosmic rays beyond that distance are, in a very real sense, invisible to us because their most energetic products are absorbed before reaching us. The detection of cosmic rays above the GZK limit, and such events have been observed, including the famous Oh My God particle detected in 1991, which carried about 3 × 10 to the power of 20 electron volts of energy, about 40 million times the energy of particles produced by the Large Hadron Collider, raises fascinating and as yet unresolved questions about the nature of these particles and their sources. The Oh My God particle was a single proton traveling at such a velocity that its kinetic energy equaled a well-thrown baseball. A single subatomic particle, carrying the macroscopic energy of a flying baseball. The physics of how something achieves that speed is one of the great unsolved problems in astrophysics. Several hypotheses have been proposed: exotic acceleration mechanisms near supermassive black holes, rare cataclysmic events, even some speculative new physics, but no consensus has emerged. Let us now take a moment to walk through what radiation actually does to a living body, because this is crucial for understanding why these cosmic environments are not merely academically dangerous but existentially dangerous. Radiation harms living organisms through several mechanisms, and the severity depends on the type of radiation, the energy, the duration of exposure, and the biological sensitivity of the tissues involved. The human body is about 60% water by mass. High-energy radiation, particularly ionizing radiation, the kind produced by all the sources we have discussed, interacts with water molecules in cells, creating reactive species called free radicals, particularly the hydroxyl radical. These free radicals are chemically aggressive and attack the nearest biological molecules, including the most critical molecule in any living cell, DNA. A single ionizing particle passing through a cell nucleus can break both strands of the DNA double helix simultaneously, creating what is called a double-strand break. Unlike single-strand breaks, which the cell can repair using the intact complementary strand as a template, double-strand breaks are far more dangerous. They can be repaired, but the repair process is error-prone, and errors in DNA repair lead to mutations, some of which cause cancer. Multiple double-strand breaks in close proximity, or in critical genes, can cause cell death or malignant transformation. At low doses of radiation, the body's repair mechanisms can handle the damage, and the long-term risk is a modest increase in cancer probability. At higher doses, the rate of damage exceeds the repair capacity, and you begin to see acute radiation syndrome, a systematic breakdown of the body's most rapidly dividing cells. The gastrointestinal lining, which replaces itself every few days, fails, causing nausea, vomiting, and eventually severe internal bleeding. The bone marrow, which produces blood cells, is destroyed, causing the immune system to collapse and the blood's ability to clot to disappear. At doses above about 4 to 5 grays, a measurement of absorbed radiation, without medical treatment, about half of all people will die within 60 days. At doses above around 10 grays, survival becomes extraordinarily rare. At doses above 50 grays, death is virtually certain and occurs within days, as even the relatively radiation-resistant nervous system begins to suffer damage. Now consider, The surface radiation at the inner edge of Jupiter's radiation belts, the Van Allen-like belts that surround Jupiter and trap charged particles in its enormous magnetic field, delivers doses of thousands of grays per day. The Galileo spacecraft, which was designed to enter Jupiter's atmosphere in 2003 and was radiation-hardened to survive significant doses, received over 3,000 grays of radiation over its mission lifetime. An unprotected human in that environment would receive a lethal dose many times over within the first few seconds. Jupiter's radiation belts, formed by the interaction of its powerful magnetic field with charged particles from the solar wind and from its volcanic moon Io, are in some ways a miniature version of the radiation environments we find around neutron stars and black holes, except compressed to the scale of a single planet. If Jupiter is already this extreme, what does that tell us about the vicinity of a pulsar, where the magnetic field is billions of times stronger? Let us not leave Jupiter without discussing what makes its radiation belts so particularly vicious compared to Earth's Van Allen belts. Earth also has radiation belts, discovered in 1958 by James Van Allen using data from the Explorer 1 satellite, the first successful American satellite. Earth's Van Allen belts consist of two concentric zones of charged particles trapped by Earth's magnetic field, extending from about 1,000 to 60,000 kilometers above Earth's surface. The inner belt, containing high-energy protons, is particularly hazardous for satellites and astronauts. Early astronauts on Apollo missions passed through the Van Allen belts rapidly, limiting their cumulative exposure to manageable levels, though the radiation exposure was not zero. Astronauts on long-duration missions aboard the International Space Station, which orbits within the lower part of the inner Van Allen belt's influence, receive radiation doses about 7 times higher than people on Earth's surface, primarily from cosmic rays and trapped particles. Jupiter's radiation belts are qualitatively similar to Earth's but differ in every quantitative measure. Jupiter's magnetic field is about 20,000 times stronger than Earth's. The belts extend much further from the planet, scaled for size. And crucially, the volcanic moon Io, one of the most geologically active bodies in the solar system, with hundreds of active volcanoes continuously erupting sulfur dioxide, constantly injects fresh ions into Jupiter's magnetosphere, keeping the radiation belts continuously replenished with lethal doses. The moon Io itself orbits within Jupiter's most intense radiation zone, and the interaction between Io's volcanic eruptions and Jupiter's magnetic field creates a spectacular electromagnetic connection, a tube of electric current, called the Io flux tube, that carries approximately 5 million amperes between Io and Jupiter's poles. This is visible from Earth as a bright spot in Jupiter's auroras. It is, in effect, a cosmic electrical circuit that contributes to the radiation environment in the Jovian system. The moon Europa, which has attracted enormous scientific interest because it likely harbors a liquid water ocean beneath its icy surface, and where some astrobiologists believe simple life might exist, orbits within Jupiter's radiation belts in a zone where the radiation dose rate on the surface is about 5,400 millisieverts per day. That is roughly 5,000 times the dose an astronaut on the International Space Station receives daily. Even bacteria, some of the most radiation-resistant organisms known, would be killed on Europa's surface after prolonged exposure at those levels. The most radiation-resistant organism ever discovered, Deinococcus radiodurans, can survive doses of 15,000 grays, a dose that would kill any other known organism many times over, because it has an extraordinary ability to reassemble its shattered DNA from multiple broken fragments. Even this remarkable microbe would be challenged by the sustained radiation environment of Europa's surface. However, and this is important, the ice of Europa's surface provides shielding. A few meters of ice attenuates the radiation dramatically, and below the ice shell, which may be several kilometers thick, the radiation levels would drop to biologically tolerable levels. The liquid water ocean beneath, protected by kilometers of ice, might be essentially radiation-free, which is why Europa remains one of the most tantalizing targets in the search for life in the solar system. The lethal radiation zone ends at the surface of the ice, and beneath it, conditions might be compatible with life. This is one of the universe's great ironies. One of the best candidates for life in our solar system exists inside one of the most intense radiation environments in our solar system. Now let us talk about something that directly affects you personally right now as you listen to this. Because radiation from space is not a distant, abstract threat. It is reaching your body constantly from multiple directions at this very moment. Cosmic rays, those high-energy particles from supernova remnants and other sources throughout the galaxy, continuously rain down on Earth's atmosphere. When they strike molecules in the upper atmosphere, they create cascades of secondary particles, showers of pions, muons, electrons, and photons that rain down through the atmosphere in expanding cones. At sea level, most of these secondary particles have lost most of their energy, and the dose they deliver is relatively small but non-zero. You receive roughly 2.4 millisieverts of radiation annually from all natural sources combined, of which about half, roughly 1 millisievert, comes from cosmic rays and naturally occurring radioactive materials. At high altitudes, where the atmosphere provides less shielding, the dose from cosmic rays increases. Airline pilots and frequent flyers receive doses several times higher than the general population from cosmic ray exposure. The crew of the International Space Station, as mentioned, receives even more. Even at ground level, you carry within your body naturally occurring radioactive isotopes, particularly potassium-40 and carbon-14, that are continuously decaying and delivering tiny doses of radiation to your tissues. Your body is mildly radioactive, as is the body of every human being who has ever lived, and this natural radiation contributes slightly to the mutation rate in your cells, and by extension, to the evolutionary pressure on our genome over billions of years. In a very real sense, the radiation from cosmic sources has been shaping the genetics of life on Earth since the first living things appeared. Mutations caused by cosmic ray interactions with DNA have been driving evolution all along. The lethal radiation zones of the universe have not only threatened life. In their diffuse, attenuated form as they reach Earth, they have helped create it. This brings us to one of the most profound questions in all of science. Where in the universe is life possible, given the ubiquity of radiation? Astrobiologists have developed the concept of the galactic habitable zone, a region within a galaxy where conditions are conducive to the emergence and persistence of complex life. The galactic habitable zone is not simply defined by distance from the galactic center, though that is part of it. At the center of the Milky Way, the density of stars is much higher, supernova events are more frequent, and the supermassive black hole at the galactic center, Sagittarius A*, with a mass of about 4 million solar masses, creates an environment of intense radiation from its activity. Stars near the galactic center are more likely to be exposed to lethal doses of radiation from neighboring stellar events, more likely to have their planetary systems disrupted by close stellar passages, and more likely to be influenced by the periodic outbursts of Sagittarius A* itself. Sagittarius A* is currently in a relatively quiet state. It is not actively accreting large amounts of material and is not producing the kind of powerful jets seen in active galactic nuclei. But there is strong evidence that it was far more active in the relatively recent past. A structure called the Fermi bubbles, giant lobes of gamma-ray emission extending about 25,000 light-years above and below the galactic plane, detected by the Fermi Gamma-Ray Space Telescope in 2010, appears to be the remnant of a period of intense activity from Sagittarius A* that occurred roughly 6 to 9 million years ago. During that active phase, the radiation environment in the central regions of the galaxy would have been dramatically more intense. Some models suggest it was intense enough to strip the atmosphere from planets within thousands of light-years of the galactic center. And this is not purely historical. In 2019, astronomers detected a burst of radiation from Sagittarius A* that was 75 times brighter than its usual output, a sudden flare of unknown cause that lasted about 2.5 hours. While this flare was still relatively mild compared to truly active galactic nuclei, it served as a reminder that our galaxy's central black hole is not dormant. It is merely quiescent. It can, and does, occasionally wake up. And the question of whether it might wake up more dramatically in the future, whether Sagittarius A* might undergo a period of activity that significantly increases the radiation environment of the galactic center, is an active area of research. The outer edges of the galactic habitable zone are defined by different considerations. Stars in the outer Milky Way tend to be metal-poor, formed from gas that had not been enriched by previous generations of stellar nucleosynthesis, and therefore lacking in the heavier elements needed to form rocky planets and the complex chemistry of life. Life as we understand it requires not just carbon, nitrogen, oxygen, and hydrogen, the four most abundant elements in living things after hydrogen, but also heavier elements like phosphorus, sulfur, iron, and dozens of trace elements. Without the enrichment of multiple generations of stellar evolution and supernova events, the raw material for life is simply not there. So the galactic habitable zone is a ring, not too close to the dangerous, radiation-intense galactic center, and not too far out into the metal-poor outer reaches. Our own solar system sits comfortably within this ring, which is one of many factors that make our location in the galaxy particularly favorable for life. But even within the galactic habitable zone, the radiation environment is not uniform. Regions near recent supernova remnants, near active pulsars, near binary systems that produce periodic X-ray bursts, are all locally more dangerous. And the galaxy's spiral arms, which our solar system passes through roughly every 140 million years as the galaxy rotates, are regions of higher stellar density, more frequent supernova events, and higher cosmic ray flux. Some researchers have proposed a correlation between Earth's periodic passages through spiral arms and peaks in mass extinction rates over geological time. The evidence is intriguing but contested, as establishing causality over hundreds of millions of years from incomplete geological records is extraordinarily difficult. Let us now venture into one of the most dramatic radiation environments in the known universe: X-ray binaries. An X-ray binary is a system consisting of a neutron star or black hole in close orbit with a normal companion star. The gravity of the compact object pulls material off the companion star, and this material falls onto the compact object in an accretion disk, radiating X-rays with extraordinary intensity. These systems are among the brightest X-ray sources in the sky, and they come in two main flavors: low-mass X-ray binaries, where the companion is a sun-like star, and high-mass X-ray binaries, where the companion is a massive, bright, short-lived star. In high-mass X-ray binaries, the companion star continuously blows off material in a stellar wind, and the compact object accretes this wind material. The X-ray luminosity of these systems can reach tens of thousands of times the total luminosity of our Sun. The most extreme members of this class are called ultraluminous X-ray sources, or ULX, and their luminosities can exceed the theoretical maximum luminosity of a single stellar mass object, the Eddington luminosity, by factors of 10 or more. Understanding how these objects exceed the Eddington limit is an active area of research. Current models suggest that the radiation in these systems is beamed in jets, so that the apparently enormous luminosity is partly a geometric effect. But even accounting for beaming, these systems are producing extraordinary amounts of X-ray radiation. A planet in a close orbit around an ULX system would be bathed in X-ray flux thousands of times more intense than the X-ray flux Earth receives from the Sun. And the Sun's X-ray output is already a tiny fraction of its total radiation. The X-ray flux from an ULX would be lethal to any life form within a very wide exclusion zone. There is also a phenomenon called X-ray bursts, which occurs in neutron star X-ray binaries when the accumulated hydrogen on the neutron star's surface undergoes runaway thermonuclear burning. These bursts are not the gentle, steady warming of a nuclear reactor but violent, sudden eruptions of nuclear fire across the entire surface of the neutron star, releasing energy equivalent to thousands of nuclear bombs every second for a period of 10 to 100 seconds. The most extreme of these, called superbursts, can last hours and release energy equivalent to the annual energy output of our Sun in a single sustained nuclear eruption on a ball of matter 20 kilometers across. If you were in orbit around a neutron star undergoing an X-ray burst, the radiation would be, to put it mildly, unsurvivable. The burst would not just overwhelm any shielding you could carry, it would likely ablate the shielding material itself, converting it to plasma. Now, let us talk about something that connects all of this cosmic radiation to our daily lives in a way that might surprise you. The technology we use to understand these phenomena is deeply intertwined with the technology that affects everyday life. The development of radiation detectors for astronomy has fed back into medical imaging technology. The CCD detectors used in telescopes are related to the sensors in digital cameras. The algorithms used to process cosmic ray data have influenced the development of machine learning. And the understanding of how radiation damages DNA, developed partly through the study of cosmic radiation effects on astronauts and through high-energy astrophysics, has directly informed cancer treatment. The linear accelerators used in radiation therapy to treat cancer operate on the same physical principles as the particle accelerators used to study cosmic rays, and the understanding of how to target radiation to destroy cancer cells while minimizing damage to surrounding tissue has grown in parallel with the science of cosmic radiation. The study of galactic cosmic rays also has direct relevance to a technological concern that is growing more urgent: the radiation environment experienced by our technology in space. Modern civilization depends on a constellation of satellites for GPS navigation, telecommunications, weather prediction, financial transactions, and military operations. All of these satellites operate in environments where radiation from cosmic rays and the solar wind continuously degrades their electronic components. Radiation hardening of satellite electronics is an expensive but essential engineering challenge, and as we push further from Earth, toward the Moon, toward Mars, toward the outer planets, the engineering challenges of radiation shielding become progressively more daunting. A crewed mission to Mars, as noted earlier, would expose astronauts to radiation doses that significantly increase their cancer risk. A crewed mission to the outer solar system, to the moons of Jupiter or Saturn, would require either extremely heavy shielding or novel approaches to radiation protection that do not yet exist. One idea that has been proposed is the use of active magnetic shielding, a spacecraft surrounded by a powerful magnetic field that deflects charged particles before they can reach the crew. The physics is sound. This is essentially replicating the Earth's magnetosphere artificially, but the engineering challenges are enormous. A magnetic field strong enough to deflect high-energy cosmic rays would require superconducting magnets of enormous size, and the system would need to operate continuously for years. Several research groups have studied this concept, including a project at CERN called SR2S, Space Radiation Superconducting Shield, but it remains a concept rather than a ready technology. Another approach involves the use of the spacecraft itself as shielding, placing water, polyethylene, or other hydrogen-rich materials around the crew habitation module. Hydrogen is particularly effective at moderating cosmic rays because the hydrogen nucleus, a single proton, is similar in mass to cosmic ray protons, and collisions between similar mass particles are particularly effective at transferring energy. This is the same reason why a nuclear reactor uses water as a moderator to slow neutrons. A spacecraft with walls made of polyethylene, essentially plastic, a few tens of centimeters thick, can reduce cosmic ray doses by a meaningful fraction, though not to the level that would make a long deep space mission fully safe by current standards. Some researchers have proposed using water walls that serve double duty as radiation shielding and drinking water reserve, though the sheer mass of water required presents significant launch cost challenges. There is also a biological approach being investigated: the identification of genetic pathways that confer radiation resistance, and the potential use of gene therapy or pharmacological interventions to temporarily boost an astronaut's resistance to radiation damage before a high-exposure phase of a mission. Research on organisms like Deinococcus radiodurans, the bacteria mentioned earlier, has identified specific DNA repair enzymes and antioxidant mechanisms that contribute to extreme radiation resistance. Some of these molecular strategies might, in principle, be transferable to human cells through genetic engineering. This research is still in early stages and faces enormous biological complexity challenges, but it represents a genuinely promising avenue. Now let us speak about one of the most spectacular and terrible radiation phenomena that operates close to Earth's doorstep in a cosmic sense: solar particle events, also known as solar energetic particle events or SEP events. These are sudden releases of high-energy particles, primarily protons and heavy ions, from the Sun, associated with solar flares and coronal mass ejections. Unlike the steady solar wind, which is relatively low energy, Solar particle events can produce particle fluxes orders of magnitude more intense over a period of hours to days. The most powerful solar particle event in recorded history was the Carrington event of September 1859. On September 1st, British astronomer Richard Carrington was observing sunspots through his telescope when he noticed a brilliant flash of white light on the sun's surface, the first recorded observation of a solar flare. Less than 18 hours later, remarkably fast, given the distance to the sun, a wave of charged particles and electromagnetic radiation struck Earth with extraordinary force. Telegraphs across Europe and North America stopped working. Some telegraph operators reported receiving electric shocks. Others found they could send and receive messages even after disconnecting their machines from their power sources, because the induced currents in the telegraph wires were sufficient to operate the equipment. The aurora borealis, the northern lights, was visible as far south as Cuba and Hawaii. Some people in the northeastern United States, awakened by the light, began preparing for the day because they thought it was dawn. If the Carrington event occurred today, with modern civilization depending on electricity grids, satellite systems, and internet infrastructure, the consequences would be catastrophic. A 2013 report by Lloyd's of London estimated that a Carrington-class event could cause between $1 and $2 trillion in economic damage to the United States alone, and that the recovery time for the most severely damaged electrical grid infrastructure could extend from 16 days to 1 to 2 years in the most severely affected regions. Some analysis suggests the damage could be even more severe, particularly to high-voltage transformers, which are manufactured in small quantities, difficult to transport, and take months or years to build. The National Academy of Sciences issued a report in 2008 warning that the societal and economic consequences of a Carrington-class event in the modern era could be comparable to those of a nuclear war, without the immediate deaths but with prolonged disruption to every system that modern life depends upon. And here is the frightening part. A Carrington-class event is not extraordinarily rare. Solar cycles run approximately 11 years, and each solar maximum, the peak of solar activity in each cycle, brings the potential for major solar particle events. In 2012, a solar eruption nearly as powerful as the Carrington event occurred, but the ejection was pointed away from Earth, and it passed harmlessly through the inner solar system without hitting us. Had it been aimed at Earth and arrived roughly 9 days earlier in its journey around the Sun, it would have struck our planet. Researchers who studied the event published their analysis in Nature Communications in 2014, and the conclusion was stark. It would have been the largest solar storm in over 150 years, possibly stronger than the Carrington event itself. We were lucky. The question is not whether another event of this magnitude will occur, but when, and whether we will be ready. The radiation environment during a major solar particle event is also directly relevant to human spaceflight. Astronauts outside of Earth's protective magnetic field, such as Apollo astronauts on their way to the Moon, would have been in serious danger if a major solar particle event had occurred during their transit. The Apollo missions were planned in part around the solar cycle, and NASA carefully monitored solar activity during each mission. On Apollo 16, in April 1972, astronauts were on the lunar surface when a major solar flare occurred. The timing was fortunate. They had already returned to the command module and begun their journey home. Had the flare occurred a few days earlier, while they were on the lunar surface without Earth's magnetic shielding, the astronauts might have received doses of radiation severe enough to cause acute radiation syndrome. In August 1972, between the Apollo 16 and Apollo 17 missions, one of the largest solar particle events of the 20th century occurred. Had any astronauts been in deep space at that time, they could have received fatal doses of radiation within a very short period. This is not merely a historical curiosity. As NASA and other space agencies plan crewed missions to the Moon and Mars, the management of solar particle event risk is one of the central radiation protection challenges. Unlike galactic cosmic rays, which are constant and omnidirectional and difficult to predict or shield against, solar particle events are transient and can be predicted with some, though imperfect, lead time using solar monitoring spacecraft. The plan for crewed lunar missions under the Artemis program includes provision for astronauts to shelter in designated storm shelters, areas of the habitat module with additional shielding, often located in the center of the spacecraft where surrounding structure provides additional protection during major solar particle events. The lead time provided by solar monitoring could allow astronauts to reach shelter before the particle flux reaches dangerous levels. Now let us journey to some of the most extreme and alien environments in the universe. Places where the radiation fields are so intense that they redefine the limits of what matter itself can withstand. We have spoken of magnetars, but let us return to them with fresh eyes, because they deserve more than a passing mention. Magnetars are the most magnetically powerful objects known to exist, and their magnetic fields produce radiation and effects that go beyond simple electromagnetic emission. The magnetic field of a magnetar is so powerful that it affects the structure of the vacuum itself. In quantum electrodynamics, the vacuum is not empty. It is filled with a constant churning of virtual particle-antiparticle pairs that appear and disappear on timescales too short to observe directly. In an extremely strong magnetic field, this vacuum activity is modified. The magnetic field influences the behavior of virtual electron-positron pairs, effectively making the vacuum birefringent, meaning it has different refractive indices for light polarized in different directions relative to the magnetic field. This effect, called vacuum birefringence, is an exotic quantum electrodynamic prediction that has been confirmed observationally in at least one neutron star system, providing a direct experimental test of quantum electrodynamics in the strong field regime. Near the surface of a magnetar, the magnetic field is strong enough to distort the electron orbitals in atoms, stretching them along the field direction into elongated cylinders rather than spheres. This dramatically changes the chemical properties of atoms, potentially making even simple molecules impossible to form in the forms we know. The familiar chemistry of life, organic molecules, amino acids, proteins, would be impossible in the immediate vicinity of a magnetar surface. The very concept of molecular structure is fundamentally compromised. This is not just a radiation hazard. It is a fundamental reorganization of the physical reality of matter. The surface of a magnetar is also subjected to extraordinary starquakes, sudden shifts in the neutron star's crust as the enormous internal stresses, driven by the magnetic field and the extreme rotation, release in abrupt slips analogous to earthquakes. These starquakes are the mechanism behind the giant flares mentioned earlier, and they are detectable as sudden changes in the rotation rate of the pulsar, called glitches, and as intense bursts of X-rays and gamma rays. The energy released in a major magnetar starquake is staggering. The 2004 event from SGR 1806-20 released about 10 to the power of 46 joules in energy. More energy in a fraction of a second than our Sun will release in its entire remaining lifetime. Let us now talk about the radiation environments around some of the most massive black holes in the universe. At the centers of many large galaxies, including our own, lie supermassive black holes, objects with masses ranging from millions to tens of billions of solar masses. When these objects are actively accreting material, they power some of the most luminous structures in the universe: quasars and active galactic nuclei. A quasar is essentially a galaxy whose central black hole is consuming material at a prodigious rate, producing radiation that can outshine the entire rest of the galaxy, containing hundreds of billions of stars, by factors of 100 to 1,000. The most luminous quasars known have luminosities exceeding 10 to the power of 14 solar luminosities, 100 trillion times the luminosity of our Sun. This radiation comes primarily from the accretion disk around the central supermassive black hole, heated to temperatures of tens of millions of degrees, and from the relativistic jets that form along the black hole's rotation axis. The inner accretion disk of an extremely luminous quasar would be one of the most intense radiation environments imaginable. Not just X-rays and gamma rays, but a sustained, omnidirectional flood of electromagnetic radiation across every wavelength, with intensities that make the surface of our Sun look cool and dark by comparison. Quasars also produce powerful winds of radiation pressure, outflows of gas driven outward from the accretion disk at velocities of tens of thousands of kilometers per second by the radiation pressure of the quasar itself. These quasar winds are powerful enough to blow the gas out of the host galaxy, quenching star formation across the entire galaxy and dramatically affecting the galaxy's evolution over billions of years. This feedback between the central black hole and the surrounding galaxy, The way in which the radiation from the quasar regulates the very conditions that created it is one of the great discoveries of modern astrophysics, first clearly recognized in the early 2000s. It means that the lethal radiation zone around an active galactic nucleus is not just locally hazardous. It is a galaxy-scale phenomenon, capable of altering the star formation rate and chemical evolution of an entire galaxy containing hundreds of billions of stars. Now I want to ask you something, because this is the kind of question that should make you pause. We understand that life on Earth exists because of a specific and very particular set of conditions. Our distance from the Sun, the presence of the Earth's magnetic field, the protection of the atmosphere, the chemistry of water. But consider, how many of these conditions are the result of fortunate shielding from radiation? The Earth's magnetic field deflects the solar wind and protects our atmosphere from being stripped away, as happened to Mars when Mars lost its magnetic field. The ozone layer absorbs the ultraviolet radiation from the Sun that would otherwise be lethal to surface life. The distance from the Sun places us outside the most intense zone of solar radiation. The thickness of the atmosphere attenuates cosmic ray primaries, so that by the time secondary radiation reaches sea level, it is within biologically tolerable levels. In how many ways is the existence of life on Earth fundamentally a story of being shielded from the lethal radiation zones that surround us? And what does that tell us about the rarity or abundance of life elsewhere in the universe? This question is at the heart of a debate in astrobiology about the Drake equation and the Fermi paradox. The Drake equation, formulated by radio astronomer Frank Drake in 1961, attempts to estimate the number of technologically advanced civilizations in our galaxy by multiplying together a series of factors. The rate of star formation, the fraction of stars with planets, the fraction of planets in habitable zones, the fraction on which life emerges, the fraction on which intelligence evolves, and the fraction that develops technology. The product is the number of active, communicating civilizations. Despite decades of research, the values of most of these factors remain highly uncertain, but the equation provides a framework for thinking about the abundance of life. The Fermi paradox arises from a simple observation. If the galaxy is billions of years old and even a small fraction of stars host technological civilizations, then some of those civilizations should have had time to colonize the galaxy many times over. Yet we see no evidence of extraterrestrial technology. The universe appears, at least to our current observational capabilities, empty of signs of intelligence. One proposed resolution to the Fermi paradox, one of many, is what astrobiologists call the rare Earth hypothesis or the gauntlet hypothesis. The idea that the conditions required for complex life are so specific and so rare that technological civilizations are extraordinarily uncommon, perhaps unique. Under this framework, the lethal radiation zones of the universe play a significant role. Most locations in the universe are far more radiation intense than Earth. Most stars are not like our Sun. Most planetary systems do not have the particular combination of factors that shield surface life from cosmic radiation. If radiation-safe zones are rare, then life might be correspondingly rare. But there is a counter-argument, and it is an important one. Life on Earth has shown an extraordinary ability to colonize extreme environments. Extremophiles, organisms that thrive in conditions lethal to most life, have been found at temperatures ranging from below the freezing point of water to above 300 degrees Celsius, in pH levels ranging from near 0 to above 13, in environments with salt concentrations 10 times that of seawater, in the deep ocean at pressures 300 times atmospheric, and in environments with very high natural background radiation. The Chernobyl exclusion zone, created by the catastrophic reactor explosion in 1986, is one of the most radiation-contaminated environments created by human activity. Yet it has become, in the decades since, a haven for wildlife. Animals do not thrive because they love radiation. They face elevated mutation rates and health effects compared to populations outside the zone, but they persist. Life finds a way, as the saying goes. More relevant to our discussion, some organisms have developed remarkable radiation resistance. We have already discussed Deinococcus radiodurans, but it is worth noting that this bacterium's extraordinary radiation resistance is thought to be a secondary adaptation. Its primary adaptation appears to be resistance to desiccation, extreme drying. And the DNA repair mechanisms that protect against desiccation happen also to protect against radiation damage. This suggests that radiation resistance can evolve as a byproduct of other selective pressures, and that life in even quite intense radiation environments might be possible, given sufficient evolutionary time. Research published in 2020 in Current Biology described the discovery of fungi in the Chernobyl exclusion zone that appear to be growing toward the most radioactive areas of the damaged reactor. Fungi that contain high concentrations of the pigment melanin and that appear to be using ionizing radiation as an energy source, the way plants use sunlight. If confirmed, and the research is intriguing but has not yet been definitively replicated, this would represent a form of radiotrophic life. Organisms that are not merely tolerant of radiation but that actively harvest energy from it. The implications for astrobiology are profound. If life can evolve to use ionizing radiation as an energy source, then the lethal radiation zones of the universe, pulsars, neutron stars, X-ray binaries, become not just threats to life but potential habitats for forms of life utterly unlike anything we know. This remains speculative, and the scientific community is appropriately cautious, but the possibility is remarkable enough to deserve mention. Now let us return to the scale of the cosmos and talk about one of the most sweeping radiation events in the history of the universe. The epoch of reionization. After the Big Bang, as the universe expanded and cooled and neutral hydrogen atoms formed, the universe entered what cosmologists call the cosmic dark ages, a period lasting from about 380,000 years after the Big Bang to perhaps 1 billion years after, during which there were no stars, no galaxies, and no sources of visible light. The universe was dark, filled with a diffuse fog of neutral hydrogen gas. Then, gradually, the first stars and the first galaxies began to form out of this gas, and they lit up the universe with their radiation. Those first stars, designated population 3 stars, were very different from stars today. Because the universe at that time contained only hydrogen and helium, all heavier elements had to be created by stellar nucleosynthesis over subsequent generations. These first stars were composed entirely of hydrogen and helium, and they were probably extraordinarily massive, perhaps hundreds of times the mass of our Sun, because without heavier elements to radiate away energy, the collapsing gas clouds fragmented less efficiently, leading to the formation of fewer but much larger stars. These massive first stars burned brightly and briefly, living for only a few million years before dying in catastrophic explosions, hypernovae, that seeded the surrounding interstellar medium with the first heavy elements and released prodigious quantities of radiation. As more and more population 3 stars formed and died, and as the first galaxies assembled, the cumulative ultraviolet radiation from these sources began to ionize the surrounding neutral hydrogen. Photons from the first stars had enough energy to knock electrons out of hydrogen atoms, turning the neutral gas into a plasma of protons and electrons. This process, called reionization, happened in a patchy, bubble-by-bubble fashion over hundreds of millions of years, as the ionized bubbles around individual galaxies grew and eventually merged until the entire intergalactic medium was ionized. The epoch of reionization, roughly spanning from 300 million to 1 billion years after the Big Bang, was one of the major radiation events in cosmic history, a period during which the ultraviolet and X-ray radiation from the first stars and the first active galactic nuclei bathed the universe in ionizing radiation on a scale that altered the chemical and physical state of every hydrogen atom in the observable universe. By the end of reionization, the universe had been transformed from a neutral, foggy state into the clear, ionized state it remains in today. The intergalactic medium is still highly ionized. Most hydrogen atoms in the space between galaxies are in the form of a plasma, and the primary reason is that the ultraviolet background radiation from galaxies and quasars continues to ionize it continuously. The universe, at the grandest scale, maintains its ionized state through the constant radiation output of billions of galaxies. The lethal radiation zones of the universe, at their most expansive, encompass the entire intergalactic medium. Let us now talk about something even more extreme, something that pushes the boundaries of our current physical theories. The radiation environment near the event horizon of a black hole. We have discussed the accretion disk, but what about right at the edge of the black hole itself? The event horizon is the boundary beyond which nothing, not matter, not radiation, can escape the gravitational pull of the black hole. At and just outside the event horizon, the gravitational tidal forces, technically called tidal forces or spaghettification, would stretch and compress any object in different directions simultaneously, tearing it apart. For a stellar mass black hole, this spaghettification would occur well outside the event horizon. For a supermassive black hole, the tidal forces at the event horizon are paradoxically weaker, because the horizon is much larger and the gradients more gentle. And in principle, an astronaut could cross the event horizon of a sufficiently supermassive black hole without immediately being torn apart, though they would have no way of knowing they had crossed it, since the event horizon is not a physical surface but a boundary in space-time. But here is something remarkable that theoretical physics predicts happens at the event horizon. A phenomenon called Hawking radiation, proposed by Stephen Hawking in 1974. Quantum mechanics and general relativity together predict that the event horizon is not perfectly quiet, that pairs of virtual particles, the same quantum vacuum fluctuations mentioned in the context of magnetar magnetic fields, can be created near the event horizon, with one particle falling into the black hole and the other escaping. The net effect is that the black hole very slowly radiates energy. It is not truly black in the quantum mechanical sense. The temperature of this Hawking radiation is inversely proportional to the mass of the black hole. Small black holes radiate at higher temperatures, large black holes at lower. For a black hole of stellar mass, the Hawking temperature is an almost unimaginably tiny fraction of a Kelvin, far cooler than the current cosmic microwave background temperature of about 2.7 K, which means that stellar mass black holes are currently absorbing more CMB radiation than they emit in Hawking radiation, and are therefore effectively gaining mass rather than losing it. Hawking radiation has never been directly observed. The effect is far too small for any current or foreseeable detector, but it is one of the most celebrated theoretical predictions in physics because it sits at the intersection of quantum mechanics and general relativity, the two great pillars of modern physics that are otherwise incompatible with each other. Understanding Hawking radiation is considered a critical step toward the development of a theory of quantum gravity. And interestingly, Hawking radiation is itself a form of radiation, specifically thermal radiation with a perfect blackbody spectrum, spanning the electromagnetic spectrum from radio waves to gamma rays, with a peak wavelength determined by the Hawking temperature. For a black hole small enough that its Hawking temperature becomes significant, a so-called primordial black hole of small mass, if any such objects exist, the Hawking radiation could be intense enough to be detectable. At the final stages of black hole evaporation, the Hawking temperature diverges and the black hole effectively explodes in a burst of high-energy radiation. Whether such an explosion has ever been observed is an open question. Now, let us spend some time on one of the most fascinating intersections of cosmic radiation in human history. The way in which our understanding of cosmic radiation has evolved, and how close we have come, on several occasions, to being seriously harmed by events we did not anticipate. Science is not a story of smooth, linear progress. It is a story of surprises, of discoveries that overturn previous certainties, of moments when the universe reaches out and reminds us how little we knew. When the Van Allen belts were discovered in 1958, scientists were genuinely surprised. There was no theoretical prediction that had definitively identified the existence of a region of trapped, high-energy particles in Earth's near space before the satellite data came in. The belts were a discovery that made the space environment suddenly more complex and more hazardous than anticipated. The early space pioneers, cosmonauts and astronauts, entered an environment that was only beginning to be understood, and the radiation hazards they faced were not fully characterized. Similarly, when the first X-ray telescopes were placed in orbit in the 1960s and 1970s, X-rays cannot be detected from the ground because they are absorbed by the atmosphere. The universe revealed an entirely unexpected menagerie of X-ray bright objects. Neutron stars accreting in binary systems, active galactic nuclei, clusters of galaxies filled with million-degree gas. The X-ray sky was as rich and complex as the optical sky, but it told a completely different story. A story of violent, high-energy processes happening everywhere, all the time. The founding of X-ray astronomy through missions like Uhuru, Rosat, Chandra, and XMM Newton has progressively revealed a universe in which extreme radiation is not exceptional but commonplace. And then there was the discovery of gamma-ray bursts, that decades-long mystery that eventually yielded to the revelation that the universe is routinely producing events of incomprehensible power, multiple times per day, scattered across the observable universe. Each time astronomers believed they had found the most extreme phenomenon in the cosmos, the universe produced something more extreme. Pulsars, then magnetars, then gamma-ray bursts, then hyperenergetic gamma-ray bursts, and now the boat GRB 221009A, which has forced theorists to revise their models of what is possible. This pattern of being surprised by the universe's capacity for violence and radiation is, in itself, a significant observation. It suggests that our catalog of extreme radiation sources is not complete. There are likely phenomena yet to be discovered, types of objects, classes of events, that produce radiation in ways and at energies we have not yet imagined. The history of high-energy astrophysics is a history of being consistently surprised by how much more extreme the universe is than we thought. There is no reason to expect that pattern to change. Let us now examine a topic that has moved from purely theoretical concern to practical urgency: the threat to Earth's biosphere from nearby astronomical events. We have mentioned the possibility of gamma-ray bursts affecting Earth, and the possibility that the End-Ordovician extinction may have been triggered by a gamma-ray burst. But there are other radiation-producing events that could plausibly affect Earth, and they are worth examining in some detail. A supernova within a few dozen light-years of Earth would be an extraordinarily dramatic event. The supernova itself, the explosion of a massive star, releases roughly 10 to the power of 44 joules of energy, with a vast majority, over 90%, emitted as neutrinos and about 1% as electromagnetic radiation, primarily in the optical and ultraviolet. The shock wave from a supernova expanding through the interstellar medium would take thousands to millions of years to reach Earth, depending on the distance, and by the time it arrived, the high-energy particles in the shock wave would have been diluted to levels that, while elevated above normal background, might not be immediately catastrophic. The more immediate concern is the prompt radiation, the ultraviolet and X-ray flash, that travels at the speed of light. Astronomers and astrobiologists have extensively studied the question of what distance would be dangerous for a supernova relative to Earth. The current consensus from research, including work by John Ellis and David Schramm published in the Astrophysical Journal in 1995 and subsequent refinements by Brian Thomas, Larissa E. Jack, and colleagues, suggests that a supernova within about 25 to 50 light-years could deliver sufficient gamma-ray and ultraviolet radiation to cause significant ozone depletion and potentially trigger a mass extinction or significant ecological disruption. Supernovae within this range are rare. The nearest massive star capable of going supernova, Ik Pegasi, is about 150 light-years away. But on geological timescales of hundreds of millions of years, the odds of a nearby supernova event increase significantly. In fact, there is direct geological evidence that the Earth has experienced elevated cosmic ray flux from nearby supernova events in the geologically recent past. Iron-60 is a radioactive isotope with a half-life of about 2.6 million years, produced primarily in supernova explosions. It should not occur naturally on Earth in significant quantities. Any primordial iron-60 from the formation of the solar system would have decayed to insignificant levels billions of years ago. Yet in the late 1990s, German researchers discovered concentrated deposits of iron-60 in deep-sea sediments dating to about 2 to 3 million years ago. Subsequent analysis has identified multiple iron-60 enhancement layers, suggesting multiple supernova events within 100 to 300 light-years of Earth within the past 10 million years. This is not a hypothesis or a computer simulation. This is physical evidence, preserved in the ocean floor, that supernovae have exploded in the cosmic neighborhood of our solar system in the relatively recent past. The cosmic ray flux associated with a supernova at, say, 100 light-years would be significantly elevated for thousands of years after the event, as the supernova remnant expands and continues to accelerate particles. Some researchers have proposed that the elevated cosmic ray flux from the supernova events recorded by ocean floor iron-60 deposits may have contributed to evolutionary pressure on early hominids, with the increased radiation driving elevated mutation rates at a time when our ancestors were already evolving rapidly. This is a speculative connection, but it is not without physical basis. It is the kind of question that illustrates how the lethal radiation zones of the universe, even at attenuated doses reaching Earth, have been woven into the fabric of our own biological history. There is another nearby stellar system that deserves mention in this context: Betelgeuse. Betelgeuse is the famously reddish star that forms the right shoulder of the constellation Orion, and it is one of the largest and most luminous stars visible to the naked eye, a red supergiant that, if placed at the center of our solar system, would extend beyond the orbit of Jupiter. At a distance of about 700 light-years from Earth, Betelgeuse is one of the nearest massive stars, and it is clearly in a late stage of its stellar evolution. It has exhausted the hydrogen in its core and is now burning through successively heavier elements, approaching the iron core that will trigger its eventual supernova. In late 2019 and early 2020, Betelgeuse underwent a dramatic dimming event. Its brightness fell to about 40% of its normal level, making it the faintest it had been in modern astronomical records. This triggered enormous public interest and speculation, including, inevitably, some premature claims that the supernova was imminent, and the scientific community scrambled to understand the cause. By 2021, the mystery was largely resolved. The dimming was caused by a large mass ejection from the star's surface that cooled into a cloud of dust, temporarily obscuring the star. This was not the precursor to a supernova, but rather a particularly large instance of the kind of mass loss that is common in red supergiants. Nevertheless, Betelgeuse will go supernova, probably within the next 100,000 years, which is very soon in astronomical terms, though it could also be tomorrow in an astronomical sense. Our ability to predict the precise timing is limited. When it does, it will be visible from Earth in daylight for several weeks, and at night it will cast shadows. It will be the most spectacular astronomical event in recorded human history. The distance of about 700 light-years is, by the calculations mentioned above, well outside the danger zone for direct radiation hazard. It would not threaten Earth's ozone layer or cause a mass extinction, but it would produce a supernova remnant in our cosmic neighborhood that would expand over thousands of years, and the cosmic ray flux from that remnant would likely be detectably elevated for much of that time. Now let us talk about something that is less well known but profoundly fascinating: the radiation environment inside stellar nurseries, the giant clouds of gas and dust where new stars are being born. These regions, called giant molecular clouds, are among the densest concentrations of material in the interstellar medium, but they are also sites of intense and complex radiation environments. Young stars, freshly formed and still surrounded by their protoplanetary disks, the disks of gas and dust from which planets form, are in many ways more radiation intense than mature stars like our Sun. They are often convectively active and magnetically turbulent, producing frequent and powerful flares. X-ray observations of star-forming regions have revealed that young stars can be orders of magnitude more X-ray luminous than their older counterparts. This has implications for planetary formation and the emergence of life. The protoplanetary disks that are the seeds of planetary systems are exposed, during the critical period of their formation, to intense ultraviolet and X-ray radiation from the young central star. This radiation affects the chemistry of the disk. It can ionize the gas, drive chemical reactions, and even photoevaporate the outer parts of the disk. The balance between disk chemistry, radiation, and planet formation is one of the most active areas of research in planetary science today. It is increasingly understood that the radiation environment during the formation of a planetary system is crucial in shaping the composition and structure of the planets that emerge from it. Moreover, the cosmic ray environment within star-forming regions is particularly intense, because many of the young, massive stars in these regions die as supernovae, producing supernova remnants that accelerate cosmic rays to high energies. This means that the radiation environment in which many young planetary systems form is far more intense than the relatively quiet environment of the mature Milky Way disk. And yet, planets form anyway, suggesting that at least some level of radiation during formation is compatible with the emergence of planetary systems, even if it influences their detailed properties. Ask yourself this as you think about all of this. What if one of the fundamental reasons that Earth developed complex life was not just the presence of the right conditions, but the specific radiation history of our solar system's formation in a particular corner of the Milky Way, at a particular time in galactic history, with a particular level of radiation exposure that drove chemistry and mutation at precisely the rate conducive to the emergence and evolution of life? Is it possible that there is a Goldilocks zone not just for temperature, not too hot, not too cold, but for radiation? Not too intense, which would sterilize, not too low, which might not drive sufficient mutation in chemistry, but just right? This idea, a radiation Goldilocks zone, is not widely formalized in the scientific literature in exactly those terms, but the individual components of the idea are all scientifically grounded. There is strong evidence that ultraviolet radiation, while lethal at high doses, plays a constructive role at low doses in prebiotic chemistry, in driving the chemical reactions that produce the precursors of life. Research by John Sutherland and colleagues at the MRC Laboratory of Molecular Biology in Cambridge, among others, has shown that ultraviolet light can drive the synthesis of nucleotides, the building blocks of RNA, from simple precursor chemicals, suggesting that UV radiation from the early sun may have been a necessary ingredient in the origin of life on Earth, rather than a simple threat to it. In this view, the radiation environment of the early Earth was not just survivable, it was catalytic. Similarly, the background mutation rate driven by cosmic rays has been an important driver of evolutionary innovation over billions of years. Without mutation, there is no evolution. Without evolution, there is no complexity. Without complexity, there is no intelligence. The same radiation that threatens individual organisms is, at the population level and over geological timescales, a driver of the very diversity and adaptability that makes life resilient. This is one of the deepest paradoxes of the lethal radiation zones of the universe. The same phenomenon that can sterilize a planet can also be a prerequisite for the emergence of life on another. Now let us turn our attention to the future, to what humanity faces as it begins, tentatively, to reach beyond the Earth into the radiation environments of space. The challenges are enormous, and they are not merely technological. They are biological and psychological and ethical. How do we decide what level of radiation risk is acceptable for astronauts? What standards should govern long-duration spaceflight to environments where the radiation exposure unavoidably exceeds the limits set for workers in nuclear industries on Earth? The current NASA standard for career radiation exposure for astronauts is set at a level that corresponds to a 3% increase in the probability of fatal cancer, a risk level chosen after extensive deliberation. But this standard was developed with low Earth orbit operations in mind, and missions beyond Earth orbit, to the Moon, to Mars, to the asteroid belt, would expose astronauts to doses that may exceed this limit, depending on mission duration and solar activity. NASA has been actively working to revise its radiation protection framework for deep space missions, and the question of how to balance mission objectives with crew health is one that does not have easy answers. Some have proposed that the astronauts selected for the highest exposure missions, perhaps a crewed Mars mission or a crewed outer solar system exploration, should be older individuals, for whom the long latency of radiation-induced cancer is less practically relevant. A 60-year-old astronaut who receives a radiation dose that increases their lifetime cancer risk by 10% faces a different practical situation from a 30-year-old astronaut who receives the same dose. This approach is ethically complex. It raises questions about discrimination based on age, about informed consent, about the social contract between a space agency and its crew members, but it has been seriously proposed in the scientific literature. Others argue that the focus should be on technological solutions. Better shielding, better predictive models of solar activity, better biological countermeasures. The development of drugs that protect against radiation damage is an active area of pharmaceutical research. Some drugs, including amifostine, a radioprotective compound already used clinically to reduce radiation-induced side effects in cancer patients, work by scavenging the free radicals produced by ionizing radiation before they can damage DNA. More advanced approaches under investigation include drugs that accelerate DNA repair or that temporarily arrest the cell cycle, preventing cells from dividing when their DNA is damaged, or that reduce oxidative stress in cells after radiation exposure. None of these approaches currently provides the level of protection that would be needed for a multi-year deep space mission, but the field is advancing. There is also interest in the use of genetic screening to identify individuals who are naturally more radiation resistant. People who carry genetic variants in DNA repair pathways that confer enhanced ability to fix radiation-induced damage. Research on cancer predisposition genes has identified a number of variants in DNA repair genes, such as BRCA1 and BRCA2, famous in the context of breast cancer risk, that, in certain combinations, significantly affect radiation sensitivity. Selecting astronauts partly on the basis of genetic radiation resistance might seem science fictional, but it is increasingly within the realm of practical possibility as genetic testing becomes more comprehensive and our understanding of the genetics of radiation response improves. But let us step back from these practical concerns and return to the grand cosmic perspective, because there is one more domain of lethal radiation that we have not yet fully explored: the radiation environment in the early universe, and the question of whether life could have existed, or might currently exist, in cosmic environments radically different from Earth's. In the very early universe, as mentioned at the start of this journey, radiation dominated. But even as the universe aged and the radiation background cooled, there were epochs and environments of extraordinary radiation intensity. The Quasar era, roughly 1 to 3 billion years after the Big Bang, was a time when the universe was smaller, galaxies were closer together, and active galactic nuclei were far more common and luminous than they are today. The intergalactic radiation background during this era was much more intense than it is now, and it is plausible that the radiation environment in many parts of the early universe was simply too intense for complex life to develop and persist, a galactic-scale version of the exclusion zone around an active galactic nucleus. Some cosmologists have proposed what might be called a temporal habitable zone for the universe, a period in cosmic history, which we may currently be in, or recently entering or leaving. When the universe's radiation environment is calm enough, its heavy element content is high enough, and its stellar population is stable enough for complex life to emerge and persist. Before about 5 billion years after the Big Bang, the universe may have been too radiation-intense and too quasar-dominated for habitable worlds to exist. Far in the future, trillions of years hence, the universe will be too cold and dark, as stars exhaust their fuel and fade, for complex life to be sustained. There is a cosmic epoch of habitability, and we appear to be living in or near its peak. This is an extraordinary thing to consider, that not only is our location in space possibly unusual in its habitability, but our location in time may also be in a privileged window. But here is where things get truly speculative, and I want to be very clear that what follows is at the frontier of scientific speculation, not established fact. Some theorists have played with the idea of life existing in extreme radiation environments, not just tolerating radiation but being fundamentally built around it. The concept of radiotrophic organisms, like the Chernobyl fungi, points in this direction, but some theorists have gone further, speculating about possible exotic life forms in the vicinity of neutron stars, life that might be constructed from nuclear rather than molecular interactions, operating on timescales billions of times faster than molecular life, since nuclear processes are billions of times faster than chemical ones, and existing in a form so alien that our conventional definition of life would not apply to it. This is deeply speculative. Some would say it falls more in the realm of science fiction than science. But the physicist Freeman Dyson, among others, explored similar ideas, and the question of whether the definition of life is narrower or broader than our experience on Earth can encompass is a genuinely open philosophical and scientific question. More concretely, there is the question of life in the accretion disks of black holes, an environment that is certainly radiation intense but that is also chemically complex, with a rich soup of molecular species, and that is in many ways not dissimilar in some aspects to the chemistry of a hot, dense nebula. Again, this is speculative, and no credible scientific model currently proposes that life as we understand it could exist in a black hole accretion disk. But the question of what forms of organization, information processing, and self-replication might be possible in extreme environments is one that scientists are genuinely working to expand their thinking about. Let us now revisit a very concrete and near-term issue: the radiation hazard to Earth from our own sun, specifically in the context of a phenomenon called a superflare. We mentioned the Carrington event as the most powerful solar storm in recorded history. But there is evidence, from the study of other sun-like stars, that stars like our Sun can produce flares far more powerful than the Carrington event, events called superflares, which release 10 to 10,000 times more energy than the Carrington event. Research by Yuta Natsu and colleagues, published in the Astrophysical Journal in 2019, used data from the Kepler Space Telescope to study sun-like stars and found that superflares occur on stars similar to our Sun with a frequency of roughly once every several thousand years. The data suggests that superflares on our Sun are not only possible but historically likely. The Sun has probably produced superflares many times over its 4.5 billion year history. The question is what the consequences of such an event would be for Earth. A superflare 10 times more powerful than the Carrington event might be survivable for Earth's biosphere. The ozone layer would be temporarily depleted over the irradiated hemisphere, and the electromagnetic disruption to technology would be catastrophic, but life itself would probably persist. A superflare 100 times more powerful than the Carrington event begins to enter territory where ozone depletion could be severe enough to have ecological consequences beyond mere technological disruption. A superflare at the extreme end of what sun-like stars have been observed to produce could, in principle, deliver enough ultraviolet radiation to cause significant biological damage to surface life during the hours or days of elevated UV exposure. This is not a theoretical concern for some distant future. It is a documented risk, studied by solar physicists and space weather researchers with increasing urgency. The question is not if it will happen, but when, and how prepared we will be when it does. The development of better solar monitoring systems, more sophisticated space weather prediction algorithms, and international protocols for grid protection and satellite safeguarding are areas of active research and policy development. The European Space Agency's Vigil mission, planned for launch in the late 2020s, is specifically designed to provide warning of solar particle events from a vantage point that allows early detection. The L5 Lagrange point, 60 degrees behind Earth in its orbit around the Sun, giving a view of the Sun's surface that would allow warning times of days rather than hours. Now I want to take a moment to describe for you, in sensory terms, what it would actually be like to experience one of these radiation events. Not as an abstraction, but as a visceral human experience. Not because any human has experienced these things, but because putting them in human terms is one of the most powerful ways of understanding their magnitude. Imagine you are an astronaut in free space. No spacecraft, no suit, just you, floating in the void. You would survive, in the ordinary way humans cannot survive in vacuum, for perhaps 15 seconds of consciousness before passing out from hypoxia. But ignore that for now. Ignore every other physical consequence of being unprotected in space. Focus just on the radiation. In normal interstellar space, well outside any intense source, you would feel nothing. The cosmic ray flux would be delivering a dose perhaps 100 times higher than on Earth's surface, but you would feel nothing at all. Ionizing radiation is invisible, odorless, silent, tasteless. It passes through you without any sensation. This is one of the most dangerous things about radiation. It leaves no immediate impression on the senses. It kills in silence. Now imagine you are transported to the vicinity of a pulsar. Not to its surface. The tidal forces and gravity would kill you instantly, but to within a few light years of a moderately active pulsar. Suddenly, the cosmic ray flux increases dramatically. Still nothing felt, but your body, at the cellular level, is beginning to sustain damage that your cells cannot repair. Every second, more cosmic ray primaries are punching through your torso, creating cascades of secondary particles, each of them shattering DNA strands, creating chromosomal aberrations. Within hours to days, depending on the pulsar's distance and luminosity, you would begin to feel the first effects of acute radiation syndrome. Nausea, fatigue, and a vague, profound wrongness in your body that you could not quite identify. Over the following days, the nausea would intensify. Your hair would begin to fall out. Your gastrointestinal tract would begin to fail. Your immune system would collapse, leaving you vulnerable to infections from your own gut bacteria, without medical intervention. And in this scenario, there is none, You would die within weeks, your body breaking down from the inside out, in a sequence that is well documented from historical radiation accidents. Now imagine you are transported to within the jet of a blazer, within the column of relativistic plasma and gamma radiation that extends from the central black hole of a distant galaxy. The change would be instantaneous. The photon flux at those energies, combined with a particle flux, would deliver doses in the millions of grays in a fraction of a second. There would be no experience. There would be no sensation of heat or light or pain. There would simply be the cessation of everything that was you, at the molecular level, faster than any nerve cell could fire a signal. Matter itself would be ionized, dissociated, and swept along by the jet. You would become, very briefly, part of the blazer, your constituent atoms incorporated into the relativistic plasma for a moment before being radiated away as photons of energy. This is the universe's ultimate statement about the limits of life. There are places where life is not merely difficult or dangerous, but where the very concept of material integrity, of any organized structure persisting through time, is negated. The lethal radiation zones of the universe are not just places where life would die. In many cases, they are places where no structure more complex than a single atom can persist for more than an instant. And yet, this is the other side of the coin. Every atom in your body was forged in a stellar radiation environment. Every heavy element you are made of was produced either in the nuclear furnaces of stars, or in the explosive nuclear crucibles of supernovae, or in the neutron-rich aftermath of neutron star mergers, all of these lethal radiation environments. The calcium in your bones was forged in a supergiant star that subsequently went supernova. The iron in your blood was created in the core of a massive star in the last seconds before its collapse. The gold in any jewelry you wear was created in a neutron star merger billions of years ago. The uranium that powers nuclear reactors on Earth was created in those same events. You are, quite literally, made of stardust forged in the universe's most lethal radiation zones. You are alive, here, now, because the universe was violent and radioactive and extreme for billions of years before your planet formed. This is, perhaps, the most profound insight that the study of cosmic radiation offers us. The radiation that kills is the same radiation that creates. The extreme energies that sterilize and destroy are also the engines of stellar nucleosynthesis, the drivers of galactic evolution, the mechanism by which the universe produces the chemical complexity that life depends upon. We are not separate from the lethal radiation zones of the universe. We are their product. We are what happens when the universe's violence is, for a brief moment and in a small corner, sufficiently attenuated by distance and atmosphere and magnetic field to allow complex chemistry to unfold. Let us discuss, now, the concept of cosmic radiation's influence on the big picture of habitability across the universe. We have been talking mostly about our galaxy, but the universe is a vastly larger place, containing an estimated 2 trillion galaxies, a number revised dramatically upward in 2016 when Consulis et al. Published a study using the Hubble Space Telescope's deep field images and found that previous estimates had missed a majority of galaxies, which are too small and faint to be easily detected. Not all of these galaxies are like the Milky Way. Elliptical galaxies, which contain a majority of the universe's stars by mass, are typically older, with less ongoing star formation, and have much lower rates of supernova activity in the present era. The cosmic ray flux within an elliptical galaxy today might be lower than within a spiral galaxy like the Milky Way. Does that make elliptical galaxies more conducive to life? Not necessarily. Not necessarily. Elliptical galaxies typically pass through an early phase of intense star formation and quasar activity. Their supermassive central black holes were active and luminous when the galaxies were young, and the radiation environment during that epoch may have been far more hostile than the Milky Way has ever been. The metal content of elliptical galaxies is generally high, providing the building blocks for rocky planets. But the orbital dynamics of stars within elliptical galaxies are more chaotic, with no neat spiral structure, and close stellar encounters are more frequent, which could disrupt planetary systems and expose them to nearby radiation events more frequently. The most hospitable regions of the universe for life may be in intermediate mass spiral galaxies like the Milky Way, at intermediate distances from their galactic centers, during the current cosmological epoch, not too early, when radiation and quasar activity were intense, not too late, in the far future, when stars have burned out and the universe is cooling toward heat death. We may live in a universe where the conditions for life are, if not unique, at least relatively uncommon among the full range of cosmic environments that have ever existed. This is a sobering thought, and also a wondrous one. Now let us talk about something that ties all of these threads together in a new and startling way. The emerging field of multi-messenger astronomy. Until very recently, almost everything we knew about the universe came from electromagnetic radiation, light in all its forms, from radio waves to gamma rays. But in September 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, ripples in spacetime itself caused by the acceleration of massive objects. The signal came from the merger of two black holes, each about 30 solar masses, located about 1.3 billion light-years away. This discovery, which earned the Nobel Prize in Physics in 2017, opened an entirely new window onto the universe. For the first time, we could see, or rather hear, since gravitational wave signals are often described using audio analogies, the universe through a sense other than light. Then, in August 2017, came GW 170817, the first gravitational wave detection from a neutron star merger, observed simultaneously in gravitational waves by LIGO and Virgo, and in electromagnetic radiation across virtually every wavelength from radio to gamma rays. This event was the moment when multi-messenger astronomy came of age. The short gamma ray burst associated with the merger, arriving about 1.7 seconds after the gravitational wave signal, confirmed the long-suspected connection between neutron star mergers and short gamma ray bursts. The optical and infrared afterglow, visible for weeks after the merger, showed the spectral signatures of heavy elements being synthesized: gold, platinum, and other R-process elements. This was the first direct observational confirmation that neutron star mergers are responsible for the production of a significant fraction of the universe's heavy elements. The implications for our understanding of cosmic radiation and its sources are profound. GW 170817 simultaneously confirmed the merger origin of short gamma ray bursts, confirmed the R-process nucleosynthesis in such mergers, and enabled new measurements of the Hubble constant, the rate of expansion of the universe, using the time delay between gravitational waves and electromagnetic radiation. Each piece of this knowledge changes our understanding of the universe's most extreme radiation environments and the processes by which those environments shape the cosmos. And there is more to come. As LIGO and its sister observatories, Virgo, Cagra, and eventually LISA in space, become more sensitive and detect more events, we will build a census of neutron star and black hole mergers in the universe, understand their rate, their distribution, and their contribution to the cosmic radiation background. This will allow us, for the first time, to calculate with some confidence how frequently civilizations like ours, if any others exist, might be exposed to the gamma radiation from nearby merger events, and what that might mean for the distribution of life in the universe. There is also the neutrino sky. Neutrinos are ghostly particles with almost no mass and no electric charge, produced in vast quantities in nuclear reactions, including those that power stars and those that occur in supernovae and gamma-ray burst jets. They interact so weakly with matter that they pass through the Earth as if it were not there. Some 100 billion solar neutrinos pass through every square centimeter of your body every second, without any effect whatsoever. Detecting neutrinos requires enormous detectors filled with highly purified water or ice. The Ice Cube Neutrino Observatory, embedded in the Antarctic ice sheet and detecting neutrinos in a cubic kilometer of clear ice, has detected high-energy neutrinos from astrophysical sources, cosmic sources far beyond our solar system. In 2018, IceCube detected a high-energy neutrino that was traced back to a blazar, TXS 0506 plus 056, which was simultaneously flaring in gamma rays. providing the first credible astrophysical source for high-energy cosmic neutrinos and opening yet another window onto the universe's extreme radiation environments. As we approach the end of this journey, I want to bring together everything we have explored and ask the most fundamental question. What does it all mean? We live on a small, rocky world orbiting an ordinary star in an ordinary galaxy, surrounded on all sides by one of the most lethal environments imaginable. Supernovae, gamma-ray bursts, magnetar flares, pulsar radiation, blazer jets, quasar winds, cosmic rays, solar particle events. The universe does not merely contain lethal radiation zones. It is, in many respects, primarily composed of them. The safe, quiet regions, the places where the radiation is attenuated to levels that permit complex molecular structures to persist and organize and replicate, are, cosmically speaking, exceptional. Earth itself is an exceptionally well-shielded environment. The magnetic field deflects the solar wind. The ozone layer absorbs UV. The atmosphere attenuates cosmic rays. The distance from the sun keeps us outside the most intense zones of solar radiation. The location in the galactic habitable zone keeps us away from the most violent zones of galactic activity. And even with all of this shielding, even in this exceptionally protected environment, we still receive a background dose of cosmic radiation that is non-negligible, that has driven mutation and evolution throughout the history of life on Earth. This should give us not only awe but also a profound appreciation for the fragility and the remarkable good fortune of our existence. We are here, alive and capable of contemplating these distant violent fires, because of a conspiracy of favorable circumstances that extend from the scale of the entire galaxy down to the scale of the individual atom. The study of the lethal radiation zones of the universe is, in this sense, ultimately a study of what makes life possible, and of what threatens it, from the most local and mundane, the solar cycle, the next solar maximum, to the most distant and catastrophic, the next nearby gamma-ray burst whenever it comes. And perhaps most importantly, it is a reminder that we are not safe by right. We are safe by circumstance. The universe does not intend to protect us. It simply has not, in this particular corner and this particular moment, aimed its most lethal energies in our direction. When we look out at the night sky and see the serene procession of stars and planets across the darkness, we are looking at a battlefield in a war of unimaginable scale, and we are standing, for now, in a fortuitous shelter between the lines. But we should not be complacent. The solar cycle continues. The galaxy rotates. Nearby stars evolve toward their end states. The future holds not serenity, but the ongoing and inevitable activity of a universe that is anything but calm. The question that every scientist working in this field is grappling with, quietly, persistently, with a kind of urgent patience, is this: how do we understand these lethal environments well enough to predict when the next one might touch us? How do we monitor the sun, the galaxy, the nearest potential sources of extraordinary radiation with enough fidelity to give ourselves the warning time we need? And how do we build, eventually, the technological and biological resilience to survive not just the quiet periods but the storms? These are not questions with simple answers. They are questions that will occupy the finest scientific minds of the coming generations. They are questions that are, in a very real sense, existential. Not in the philosopher's casual use of that word, but in the literal, biological, species survival sense. The lethal radiation zones of the universe are real. They are documented. They are active. And some of them, at some level, are aimed at us, or will be. Now, as we approach the very end of the story, there is one more thing that deserves to be said. Something that puts all of this danger and violence and cosmic indifference in a slightly different light. There is a theory, again, a theory speculative but taken seriously by a number of researchers, called the Nemesis hypothesis. It proposes that our sun has a distant companion star, perhaps a red or brown dwarf, in a wide orbit that brings it periodically into the outer solar system on a timescale of roughly 26 to 30 million years. The passage of this hypothetical companion through the Oort cloud, the shell of comets at the outermost edge of the solar system, would periodically disturb comet orbits, sending showers of comets into the inner solar system. Some of these comets would strike Earth, causing impact winter and mass extinctions. The proposed periodicity of 26 million years was identified by researchers David Ropp and Jack Sepkoski in 1984, who found a statistically significant pulse in the frequency of mass extinctions in the fossil record at approximately that interval. The Nemesis hypothesis was proposed to explain this pattern. No companion star has ever been detected. Surveys of the solar neighborhood, including comprehensive sky surveys by the WISE infrared telescope, have found no candidate, and most astronomers do not believe Nemesis exists. But the underlying observation, a possible periodicity in extinction events, remains intriguing and not fully explained. And it connects, in the radiation story, through a different mechanism. Some researchers have proposed that instead of a companion star, the periodicity might reflect the solar system's oscillation through the plane of the Milky Way, which rises and falls above and below the galactic plane on a timescale of roughly 30 million years. Each passage through the denser galactic midplane would expose the solar system to a higher density of molecular clouds, more frequent stellar encounters, and a higher cosmic ray flux. This is a more tractable hypothesis observationally, and while the evidence for the extinction periodicity itself is debated, some paleontologists question the statistical robustness of the Ropp-Sepkoski data. The idea that galactic dynamics might influence Earth's extinction record is taken seriously by enough researchers to remain in active scientific discourse. This is the universe's long game. Not just the instantaneous violence of a magnetar flare or a gamma-ray burst, but the slow, rhythmic, glacial influence of galactic structure on the geological and biological history of a small planet. The lethal radiation zones of the universe do not just act on timescales of seconds and minutes. They act on timescales of tens of millions of years, quietly shaping the evolutionary history of life through modulations in cosmic ray flux and stellar encounter rates that leave no obvious fingerprint, no crater, no iridium layer. But that may have, over the grand sweep of geological time, redirected the course of evolution again and again. If you have stayed with this story to this point, I want to leave you with something. Not a fact, not a statistic, but a feeling. The feeling of standing at the edge of the observable universe with full knowledge of what lies out there. Not the serene, static picture of stars and galaxies that a casual glance at the night sky might suggest, but the roiling, violent, radiation-drenched reality of a cosmos that is simultaneously our home and our greatest existential challenge. We built telescopes. We launched satellites. We buried detectors in Antarctic ice and developed kilometer-scale gravitational wave observatories, and pointed our most powerful instruments at the most violent corners of the cosmos. And in doing so, we discovered that the universe is not a friendly place. It is not designed for us. It is not arranged for our comfort or our survival. But it is breathtakingly, overwhelmingly, inexhaustibly interesting. Every gamma-ray burst is a message from the universe written in the most energetic language it knows. Every pulsar is a lighthouse in the dark, rotating with terrifying precision, warning of what lies in the vicinity of dead stars. Every magnetar flare is a reminder that magnetic fields can reach energies so extreme that our everyday physics breaks down and new physics takes over. Every cosmic ray that passes through your body. Right now, as you listen to this, one or two of them are transiting your body every second, carries information about its source in the far reaches of the galaxy, encoded in its direction and energy, waiting to be read by detectors sophisticated enough to decode the message. We are, in this sense, embedded in the universe's radiation. We cannot escape it. We can shield against it, attenuate it, monitor it, study it, and in small ways manipulate it. But it is part of us, as we are part of it. The iron in your blood carries the atomic fingerprint of a supernova that lived and died billions of years before Earth formed. The DNA in your cells has been shaped by billions of years of cosmic ray bombardment, each mutation a tiny contribution from the galaxy to the project of life. The next time you look up at the night sky, you will not just be looking at stars. You will be looking at the sources of the energies that made you, the forces that have threatened your ancestors throughout the history of life, and the ongoing fires of a universe that has never once, in 13.8 billion years, stopped burning. Think about that the next time the night seems peaceful. Think about what is really happening out there, behind the quiet veil of darkness. Think about the magnetar flaring on the other side of the galaxy, right now, releasing more energy in a second than you can comprehend. Think about the gamma ray burst that fired its lethal beam into the cosmos 2 billion years ago, whose radiation is, at this very moment, traveling toward you at the speed of light, though it will not arrive for another 2 billion years. Think about the pulsar sweeping its beam through the galaxy like a cosmic lighthouse, indifferent to anything in its path. And ask yourself this final question. Given all of this, all this violence, all this radiation, all this cosmic indifference, isn't it extraordinary that you exist? Isn't it extraordinary that in a universe so thoroughly and fundamentally lethal, life found a way? Isn't it extraordinary that consciousness, which is to say the ability to contemplate the universe, to measure it, to marvel at it, emerged from the same violent processes that are capable of destroying it in an instant? The answer to that question, whatever form it takes for you, is the beginning of a conversation that science is only just starting to have. A conversation about what life is, where it can exist, how rare or common it might be in a universe that is fundamentally about energy and radiation and the transformation of matter. A conversation about what it means to exist in a cosmos that does not know you are there, and that would not change its behavior one iota if it did. The lethal radiation zones of the universe are not just a story about danger. They are a story about creation, about history, about the deep connection between the most violent processes in the cosmos and the fragile, improbable phenomenon of life. And that story is far from over. The next discovery, the next giant flare, the next record-breaking gamma ray burst, the next gravitational wave signal from a neutron star merger, the next unexpected iron 60 layer in the ocean floor, will add another chapter. And each chapter will change, in some fundamental way, what we thought we knew. We are on the edge of something. We always have been. The universe does not wait, and neither should we. The next alarm has already been set. The next lethal pulse of radiation has already been launched from some unseen corner of the cosmos. And somewhere, someone is building the detector that will see it coming. The question is whether we will be ready. The question is whether, when the universe next speaks in its most violent voice, we will have the wisdom and the technology and the sheer stubborn human determination to listen, to understand, and to respond. That is not a story that ends here. That is a story that is happening right now, in real time, in every observatory and laboratory and satellite control center on this planet. It is the most important story there is. And you are, whether you knew it or not, already part of it. Every person who looks up at the night sky and wonders, every person who asks why the stars shine the way they do or what happens when they die, every person who feels that pull of curiosity and awe toward the vast dark, every one of them is participating in the human project of understanding the lethal radiation zones of the universe, and understanding them, against all odds, in time to matter.